Almost every sufficiently distant galaxy we observe is receding from us. Not only the galaxies nearby, but almost every distant galaxy in almost every direction. And in general, the farther away a galaxy is, the faster its recession appears to be. That immediately suggests a question. If the distances between galaxies are increasing, then surely the universe must be expanding into something. An empty region, a larger void, a container waiting to be filled. It seems like the only logical possibility. It is not. The reason takes us to one of the most disorienting ideas in modern cosmology. The universe is not expanding through a pre-existing space in the same way that an explosion expands through a room. On the largest scales, the geometry that defines distances between galaxies is changing with time. Once we let go of the idea that space is a fixed, empty container, the question, what is the universe expanding into, does not receive a conventional answer. It is replaced by a better, stranger question. What does it mean for space itself to evolve? This is what we are going to resolve. If the universe is expanding, what is it expanding into? By the end of this video, you will understand why that question contains a hidden assumption, why cosmic expansion is not simply movement through an external space, what cosmological redshift actually tells us, and why galaxies can recede from one another, even though none of them occupies a special central position. You will also understand why the expansion affects the largest cosmic scales, while leaving galaxies, solar systems, and atoms essentially unchanged, why the observable universe can have a present-day radius of roughly 46 billion light-years, even though the universe is about 13.8 billion years old, and what dark energy has, and has not, explained about the future of the cosmos. Let us begin with why this matters. The expansion of the universe is not an obscure theoretical detail. It is supported by several independent lines of observation, including the redshift of distant galaxies, the cosmic microwave background, the distribution of galaxies across cosmic time, and measurements of distant supernovae. These observations influence how we estimate the age of the universe, how we reconstruct its history, how we describe the geometry of space and time, and how we think about its long-term future. If we misunderstand what expansion means, nearly every other conclusion in modern cosmology becomes harder to understand. But before we discuss the physics, we need to confront the intuition that makes this subject so confusing. Almost everyone pictures cosmic expansion in the same way, as an explosion. Matter begins at one central point and flies outward into an empty space that was already there, like an explosion inside a vast room. In this picture, the room existed first. The explosion simply filled more and more of it as time passed. This image treats space as a stage, a fixed backdrop that exists independently of everything happening inside it. It is the same basic intuition we questioned in our earlier episode about time and gravity. That intuition is not unreasonable. It matches every ordinary explosion we have seen. Fireworks expand into a sky that already exists. Shrapnel moves through air that surrounds it. Nothing in daily experience prepares us for the possibility that the room itself, the space, could be dynamic. But in general relativity, space is not merely a passive background. Space-time has a geometry, and that geometry can evolve. A useful metaphor is a loaf of raisin bread rising in an oven. As the dough expands, every raisin becomes farther from every other raisin. The raisins are not necessarily moving through the dough in the same way that objects move through a room. Instead, the distances between them increase because the dough between them expands. A raisin near the edge of the loaf does not occupy a special cosmic center. From its perspective, the other raisins recede. A raisin that is farther away appears to recede faster because there is more expanding dough between the two raisins. This is a useful analogy for the relationship described by the Hubble-Lemaître law, but the analogy eventually breaks down. A real loaf has an outer surface and expands into the air surrounding it. The universe, according to current cosmological models, does not require an equivalent external space. What the physics actually tells us is more precise. In general relativity, the metric is the mathematical structure that specifies distances and times. In cosmology, the large-scale metric can change as the universe evolves. Cosmic expansion refers to this changing scale of distances between sufficiently separated, co-moving points, not to galaxies flying outward through a static container toward an external edge. This does not mean that galaxies have no motion of their own. Galaxies can move locally under gravity, orbit one another, merge, and possess what cosmologists call peculiar velocities. But on sufficiently large scales, the expansion of the universe dominates the average relationship between distant galaxies. This distinction changes everything. There was no localized explosion at one point inside a larger empty room. In the standard, homogeneous and isotropic description, the large-scale expansion occurs throughout space. Every observer in a sufficiently large representative region would see distant galaxies receding in a pattern similar to the one we observe from Earth. This is not because Earth sits at the center. It is a consequence of the large-scale geometry of an expanding universe. The strongest early evidence came from redshift. When a source moves through already existing space, its light can be Doppler shifted, just as the pitch of an ambulance siren changes as the ambulance passes by. But the redshift seen in distant galaxies is not simply ordinary Doppler motion. Cosmological redshift occurs because the wavelength of light increases as the light propagates through evolving space-time while the universe expands. A spectral line emitted at one wavelength can arrive at a longer wavelength because the scale of the universe changed during the light's journey. In real observations, cosmological redshift can be accompanied by local motion and gravitational effects. But on the largest scales, the systematic relationship between distance and redshift reveals the expansion history of the universe. In 1929, Edwin Hubble published observations showing that the redshift of distant galaxies generally increased with distance. The relationship became known as Hubble's law and is now more accurately called the Hubble-Lemaître law, reflecting the contributions of several researchers to the discovery and interpretation of cosmic expansion. Hubble's observations were revolutionary. They transformed the universe from a seemingly static backdrop into a cosmos with a history. But the observations alone did not instantly settle every conceptual question. A relationship between distance and recession could initially be described either as galaxies moving through a static space or as the large-scale geometry of space evolving. Theoretical work based on Einstein's equations, together with decades of additional observations, showed which description fits the full body of evidence. When general relativity is applied to a universe containing matter and energy distributed approximately uniformly on large scales, its equations allow the cosmic scale factor to change over time. The universe can expand, contract, or remain momentarily static, depending on its contents and initial conditions. Physicists including Alexander Friedmann and Georges Lemaître developed important early solutions to these cosmological equations. Later, the discovery of the cosmic microwave background in 1965 provided evidence that the universe passed through an early hot, dense phase. The modern picture is not based on one observation alone. It emerges from the combination of galaxy redshifts, the cosmic microwave background, the abundance of light elements, the large-scale distribution of matter, and other observations across cosmic history. Now we can return to the original question. If distant space is expanding, what is it expanding into? What lies beyond the edge into which the universe is spreading? The problem is that this question assumes space must be embedded in a larger container. It imagines that space is a substance located inside something bigger, like the loaf expanding into the kitchen air. But general relativity does not require an external container. In the theory, space is not a material object sitting inside a larger room. It is the geometric relationship between events and locations. Those relationships can change with time without requiring an external region for the universe to fill. This may sound like a semantic trick, so consider another metaphor: the surface of an inflating balloon. Imagine two-dimensional beings living entirely on the balloon's surface. They cannot see the inside or the outside. As the balloon inflates, every point on the surface becomes farther from every other point. The inhabitants can describe the changing distances using only measurements made within their own surface. From their perspective, the surface does not need to expand into anything. Their entire physical space is the surface itself. The metaphor is useful because the surface has no special central point within the two-dimensional geometry. Every observer sees distant points receding in the same large-scale pattern, but the metaphor must be handled carefully. Our universe is not necessarily the three-dimensional surface of a balloon, and current cosmology does not require a higher dimensional external space in which our universe is embedded. The geometry of the universe may be spatially flat, positively curved, or negatively curved. It may be finite or infinite. A finite universe can also be unbounded, meaning it has no edge that an observer could reach and cross into an outside region. These are questions for geometry, not for visual intuition. The important point is this: the mathematics describing the universe does not need a surrounding room. Cosmic expansion, therefore, does not mean that everything is becoming larger in the same way. Galaxies, stars, planets, and atoms are held together by forces that dominate over the extremely gentle effect of cosmic expansion at local scales. Gravity binds solar systems and galaxies. Electromagnetism binds atoms and molecules. The strong nuclear interaction binds atomic nuclei. On these scales, local forces prevent objects from simply following the large-scale expansion. The expansion becomes measurable primarily across enormous distances between gravitationally unbound galaxies and galaxy clusters. This is why the Milky Way, the solar system, and your own body are not being stretched apart by cosmic expansion in any meaningful everyday sense. The universe can expand on large scales while local structures remain stable. There is another distinction that often causes confusion. The observable universe is not necessarily the entire universe. The observable universe is the region from which light or other signals have had time to reach us since the early universe. The age of the universe is approximately 13.8 billion years, but the present-day proper distance to the edge of the observable universe is roughly 46 billion light-years in standard cosmological models. This does not mean that light traveled 46 billion light-years through unchanging space. Light traveled for billions of years, while the geometry of the universe continued to evolve, increasing the present-day distance between us and the regions where that light was emitted. Beyond the observable universe, there may be much more universe. It could be finite or infinite. We do not know from observation alone. Some regions may also be permanently beyond our ability to receive signals because of the expansion history of the universe. The observable universe is not the edge of everything that exists. It is the limit of what can currently be observed from our particular location and time. Now we reach the part where established evidence must be separated from open questions. The universe is expanding, and the large-scale expansion is best described by the evolution of the metric rather than by galaxies moving through a fixed background. This is supported by a broad network of observations and by the success of general relativity and modern cosmological models. What remains less settled is why the expansion began accelerating. Observations of distant Type Ia supernovae in the late 1990s showed that the expansion has not simply continued at a constant rate. On cosmic timescales, the expansion appears to be accelerating. Scientists use the term dark energy for whatever component of the universe is responsible for this behavior. Within the standard cosmological model, dark energy accounts for approximately 68 to 70% of the universe's total energy density. But this percentage is a model-dependent estimate, not a direct photograph of a substance. We know that the accelerating expansion is real within the current evidence base. We do not yet know the fundamental nature of dark energy. It could be associated with vacuum energy, a cosmological constant, a new dynamical field, or, if future evidence requires it, a modification of gravity on cosmic scales. These possibilities remain active areas of research. We also do not know with certainty whether the universe as a whole is infinite or finite, but unbounded. Current measurements indicate that the spatial geometry of the observable universe is very close to flat, but spatial flatness alone does not determine the entire global topology or total extent of the universe. So let us bring the argument together. The universe is not expanding into anything in the ordinary sense, because that question assumes a larger pre-existing container. General relativity does not require such a container. Space is not a fixed stage on which cosmic events unfold. It is part of the physical geometry of the universe, and the distances defined by that geometry can evolve. Distant galaxies are not, for the most part, flying outward from a central explosion through empty space. They have local motions, but on the largest scales, their separations increase because the cosmic metric evolves. There is no special center of the expansion within the universe, and there is no known outer edge toward which all galaxies are traveling. The deeper lesson connects directly to the earlier episodes in this series. Gravitational time dilation revealed that time is not a universal backdrop shared by every observer. Entanglement revealed that spatial separation does not guarantee independent quantum properties. Cosmic expansion reveals that space itself is not the passive, empty container our everyday experience teaches us to imagine. Time, separation, and space feel like the most basic features of reality. Yet at the deepest levels, they are dynamic, geometric, and connected to the physical contents of the universe. That leaves us with one more question. If space and time are dynamic and shaped by the physical state of the universe, what happens when we push these ideas backward toward the earliest moments we can describe? What can physics really say about the origin of space, time, matter, and energy? That question will take us from the expansion of the universe today to the beginning of cosmic history. This has been Planck's Edge. Thank you for stepping past the edge of what you thought you knew about space, expansion, and the shape of the universe.